This is 5.2, day 2, part 1. We're going to continue with 2 more examples where we verify that the left and the right side of the equations do in fact equal each other using our identities from our gold sheet. Here's our first example. We're going to start with the left-hand side of this equation. And we want it to get to be like the right-hand side. So we're trying to prove that the tangent of x plus the cotangent of x does in truly fact equal the secant of x times the cosecant of x. And I gave you a hint there. Convert everything to sines and cosines. So we're going to start with the left-hand side. And again, what I have in the blue writing, you don't have to do for your homework. You don't have to even do for a test or a quiz. We will be able to, as teachers, recognize when you do the next step if you've done it correctly. If you replace one piece with the correct identity, then you're fine to go. So what might I want to do with that tangent of x or that cotangent of x? 1 over tangent of x with cotangent of x? Okay, that's a good start. What else might you want to do? What's another thing you could do? Put them into sines and cosines. So what identity would help us to get us into sines and cosines? And that would be multiple identities. So looking on your gold sheet, what can I replace tangent of x with? Very good. I can use the quotient identity. The tangent of x equals the sine of x over the cosine of x. So I just took that left side and just rewrote it. And now identify that the tangent of x is sine of x over cosine of x. And the cotangent of x is also can be rewritten as with the quotient identity. And what's that one? 1 over tangent is the reciprocal identity. Very good. Quotient identity again says that now it's cosine of x over the sine of x. So here's the quotient identity and the quotient identity. Now remember, my right-hand side is a product of 2 terms. And on my problem right now, I have 2 terms that are adding together, and I want to get them into 1. So a lot of times when you see 2 fractions or 2 terms, a lot of times you have to add them together. Can I add these 2 fractions together as they are? No, they're unlike denominators. So what do you do if you have unlike denominators? Find the least common denominator. What is going to be the least common denominator? Both of them. There's nothing in common. So if we talk about that first fraction on the left, what am I missing on the left-hand side? I'm missing the sine of x. So in this first fraction, I'm missing the sine of x. So I have to increase that first fraction by the sine of x and the sine of x. In the right-hand side fraction, what am I missing? Yeah, I need to have the cosine of x. So I'm going to increase the second fraction by a cosine of x and a cosine of x. And the first fraction by a sine of x and a sine of x. Now are the 2 fractions exactly alike, having denominators exactly alike? Yeah. Yes. So we can combine them into 1 fraction. I also multiplied the sine of x's together here. The sine of x times the sine of x is sine squared of x. So some of you might do this in 1 step. I did it in 2. And then cosine of x and cosine of x is cosine squared of x. So I multiplied first. But you could have multiplied in this step and combined them into 1 fraction. It's how comfortable you are with it. So now we're at this point. We have the 2 fractions combined into 1 fraction. Now that nice Pythagorean identity pops up in the numerator. What do I replace that numerator with now? With 1. Awesome. sine squared of x plus cosine squared of x equals 1. Now I have 1 over the cosine of x times the sine of x. Who can help me out next? What might be the next step for us? Yes, use the reciprocal properties. So I added an extra step in here that you might not need, which is fine. I separate out that fraction into 2 separate fractions that are multiplied together, so I can see those reciprocal identities. What is 1 over the cosine of x? What is its reciprocal? Secant of x. What is 1 over the sine of x? Cosecant of x. 1 over the sine of x is cosecant of x. Did we now verify that the left side does in fact equal the right side? Yep, we are done with this problem.
Do you ever get one and get home?
Not in this book, no. If you did, then you have to go back and start over again, most likely. Or go back in a previous step if you get stuck. Okay, last problem. We haven't seen one like this question yet. Sometimes it's a good idea to multiply the numerator and a denominator of a fraction by kind of think of it as like your common denominator of like your complex conjugates when we were dealing with imaginaries or radicals when you're trying to rationalize the denominator. So we're going to work with the right-hand side of this question.
We chose the right side of this, like how do you know when the dot is the right side?
About 90% of the time, it's the left-hand side. You try to pick ones that have like the most difficult looking side. Like the longest is usually it as a hint for you too. So we're going to work with the right-hand side. So I just rewrote the right-hand side again. And here's the first step in the blue. When I multiply by like the complex conjugate, before I always change that second term sign. So if I look at 1 minus the sine of x, it's like conjugate would be 1 plus the sine of x. And there's going to be a nice thing that happens when we multiply like complex conjugates. Remember those middle terms always canceled out when we FOILed them in the denominators? And what's going to appear then is a sine squared of x. And that's leading us into our Pythagorean identities again. So I'll give you a little bit of time to catch up with this question. And then we're going to multiply these two fractions together. So we're going to multiply across.
So how did you get that one?
I took the kind of like a complex conjugate. Here's my denominator. I would multiply by 1 plus the sine of x to the both numerator and denominator. So you're changing it, but it's only really increasing it by itself 1. So I just rewrote that same step again, telling you the two things that we're going to do next. We're going to distribute this numerator. So when we distribute it, we multiply the cosine of x times 1, and then the cosine of x times the sine of x. In the denominator, we FOIL, but since they're kind of like complex conjugates, the middles cancel out, so it saves us some time. Now Pythagorean identity popped up in the denominator. So 1 minus sine squared of x. 1 minus sine squared of x is cosine squared of x. That green piece is a Pythagorean identity that can replace with cosine squared of x. Now there's lots of cosines of x's in that problem now. What might I want to do next? Just hit it for a second so you wouldn't see it. What might I want to do next? Before I can cancel, though, I can't cancel quite yet because there's a plus symbol here. Greatest common factor, I could greatest common factor that cosine of x out and then cancel. Or I can separate the fractions back out again. Because the beginning of this problem was a secant of x plus the tangent of x, two separate terms. So I'm going to go back again now and separate them back out. And that allows me now to cancel. What can I cancel from the first fraction? That left-hand side. So if I separate those two fractions out, what cancels in the first fraction, the left one? A nice cosine of x. So if I reduce this by a cosine of x, this is just now a cosine of x, and this becomes a 1. If I go over to the right one, the right fraction, I can also cancel a cosine of x out. So now it looks like this. So now I have 1 over the cosine of x plus sine of x over cosine of x. Two more identities pop up. The left one is the reciprocal identity, and the right one is the quotient identity, which is the secant of x plus the tangent of x. Good? Here is what your assignment will be today on 5.2 day 2. 11 through 21 odd, 25, 27, and 29.